Jeevan, you are going to present something or? It is showing Jeevan is presenting. Jeevan, why you are going to presenting? Anything you are going to present? Sir.
Good morning, sir.
Yeah, good morning. Good morning. I can see you. Yeah, good morning. Thank you. Thank you.
Yes, sir. Sir, can we
So am I
start,
audible
sir?
clearly? Yeah, good morning, Dr. Asha Rani and Dr. Avatpati. I can see you. And I think we're the only four by now. And the rest of the people, they're connected or I mean, it's live streamed or what it is?
Yes, yes, sir. It is a live stream on YouTube, sir. They are.
Okay.
We have posted a link to them, sir.
Okay, that's fine. That's fine. So, so whatever is being presented, so it's audible and they can see it also, right?
Yes, sir. Yes, sir. They are looking there, sir, on YouTube, sir.
Okay.
Yes, sir.
Okay,
Even
fine.
sir, even sir, suppose any participant having some queries, they will post on the chat
Yes.
box, and
Okay.
we people finally we have to posted you which kind of question they are asking
At the
Okay,
end
so
of
you
the
will
session.
take up the question.
at the end of the class, sir.
Yeah, that's fine.
Okay, sir. Okay, sir.
So I'm ready from
Welcome.
my side. It's okay. Okay, yeah.
Okay, sir. Thank you, sir. Welcome to all the participants from India and abroad, and our eminent speaker of today's first session. It's our privilege and honor to introduce Professor Sathans from NIT Kurukshetra, speaker of the first session in the second day of the program on the topic of intelligent control and its application in microgrid. He has received PhD degree in electrical engineering from the NIT Kurukshetra, where he is currently a professor in the Department of Electrical Engineering. He has more than 25 years teaching and administrative experience. He is a member of IEEE and ISTE and various other organizations. His area of research interest includes intelligent control and its application, automatic generation control, power electronics, advanced control application in power system, robotics, smart grid, and wind energy conversion system. He has served as dean for 3 years and is currently serving as the coordinator, technical education quality improvement program 3 at NIT Kurukshetra. At the national level, he has served for 3 years as the chairman of All India Board of Technician Education of AICTE, New Delhi, and also as the president's nominee for faculty selections at NITs across the country. He has traveled to USA, Australia, France, UAE, Canada, and Japan for various academic interaction and has delivered talks in reputed international conferences. He has got many publications to his credit in different international, national journals and conferences. He has published more than 70 publications in reputed journals and conferences. He has supervised more than 8 PhD scholars and more than 45 MTech scholars. He has delivered many invited talks and chaired technical sessions in national, international conferences. He is reviewer of different journals, conferences of repute. Apart from these, he has received various awards in academic and in administration from national and international organizations. I only counted few, but there is a long list for his creditability. Once again, sir, I welcome you, sir. Now we can start the session, sir. Thank you.
Okay. Thank you, Dr. Jeevan Jyoth. In fact, I don't know whether I deserve all that, nice words, but it's fine. Thank you so much for, your nice introduction. And yes, good morning to all the participants. I believe that I'm audible to you very clearly. That maybe Jeevan Jyoth can endorse. I mean, it's absolutely clear.
Yes, sir. Yes, sir.
Am I audible to
It's,
you? Okay, thank you.
yes, sir. Yes.
Thank you. So I start with my presentation. I'll share the presentation, and then we'll start this session. All right.
Yes, sir. Sure, sir.
So,
There is the option, sir. Present now.
yeah, I know. Is it visible? Jeevan, is it visible?
Yes, sir. Yes, sir. It is. This is
Okay. So thank you. So good morning once again to all the participants, and I welcome you to my session. And that's on intelligent control, a bit of an overview and what are the issues therein, and what are the potential applications of intelligent control. So when we try and understand the very meaning or very purpose of, intelligent control, so what do we understand by this term, right? So if we think of the control system in general, so control system is something, there's a system wherein some parameter of interest or some variable of interest is being controlled by way of using certain controller. And system, as all of you might be knowing, is the combination of some physical components which are interconnected with each other or which are joined with each other in such a way, in such a fashion, that that particular interconnection, which is in fact very systematic, results into certain specific goal. Right. So in that system, in case there is a parameter, at least one parameter of interest to you, or any, whatever that variable is, which is under control, then that system in a way can be termed as a control system. Something is being controlled, and some variable, some parameter is being controlled by way of using certain techniques, controllers, right? And PID, the three-term controller, is very, very popular, and it has been into practice for so many decades, and it has been, in fact, effectively being used and has been used. And other than that, there are a lot of other techniques, conventional, modern, until you have you might have heard of the conventional controller, the the nonlinear controllers, the adaptive controllers, MRAC, sliding mode, robust, and all and all. Likewise, we have the intelligent controller as well. But when we say intelligent control, that doesn't mean the other control, that has been into practice for so long, and even today is not intelligent, right? Or is not good, maybe. So this is just the name given for some reasons, right? It is kind of not a comparative analysis. Okay, one category of control system is not intelligent, this is intelligent. No. Okay, so we'll understand this term as we go by in the presentation. And I'll take you through my session around these points, brief introduction to what it is. Just to give you a flavor of the term intelligent control. Then what are the characteristics of intelligent control techniques? Right. What are the different features of these techniques? Then applications of intelligent control. Where all could we make use of these techniques? Why the need for intelligent control? Yes, in the first place, we need to establish that in case we are using certain techniques, so there has to be a reason for, right? It's just not that you can use any technique anywhere and everywhere. It doesn't go that way. So so why the need for this, and when and where to use these techniques? It's also not that that intelligent control is a kind of a panacea. You can use it anywhere and everywhere, and you'll get better results. Not like that. So we'll try and understand that aspect as well. Why the need for, and if at all the need is there, then where, in what kind of situations should we be using these techniques? Then intelligent control basic techniques, the fundamental ones, to begin with, in fact. So they are neural network and fuzzy logic. They are the core constituents of intelligent control techniques. And obviously then the combinations, the complementary use of these techniques, or in synergy, neurofuzzy systems like that. Then what are the limitations and plus points of these techniques, neural network, fuzzy logic, etc. And GAI I just picked up, otherwise there are a lot of evolutionary algorithms, but then this was almost the first one, so thought to have some discussion around that. And then I'll pick up one case study example wherein, the work done by one of my students. So I'll say that, wherein we have used this intelligent control technique. Okay. So, what is intelligent control? Do intelligent controllers exist? That's a question. So, to that question, the answer is obvious. Yes, they do exist, and that's why there's this session, in fact, on. So, so intelligent controllers, they do exist. We do take, do exercise intelligent control almost every day in our life. If we, as a human being, consider ourselves as a controller, as a system, then we do take intelligent decisions almost every moment. So, for example, if you were to control something, you would call yourself as an intelligent controller, right? Say the act of balancing, walking, learning, driving. Whenever you're doing any of these activities wherein some intelligent decision is being taken every moment, right? Then, if you're able to handle that nicely without the number crunching game, or without the intense mathematical computations, as a human being, we do not need to be doing those computations, but then we are able to take all these decisions very nicely. We can drive a vehicle through whichever way, but then everything it's a closed loop control. We are getting the feedback through our eyes. Brain is there, working as a controller and doing everything nicely. So as a biological system, we can call ourselves as an intelligent controller. Okay, example, control of a child's behavior. Yes, child's behavior, the mothers may appreciate this maybe a little better. A child could be termed as an uncontrollable system, unobservable system, stochastic, non-linear, and whatever, and sometimes unstable as well. So if somebody can control the child and and be around, and the behavior of the child can be controlled, then fine. That person who is controlling, maybe a mother or a father or a brother or a sister, could be termed as an intelligent controller, so to say, onto that. The most successful control systems on earth are biological ones, right? So nature has a lot of things for us to learn from, right? Nature, teaches us so beautiful, balance in this on this planet, and there are a lot of intelligent behaviors there in nature that you can observe, and based on those very intelligent behaviors, based on the very intelligence present in nature, right, in so many biological creatures or otherwise, we need to learn from that. Based on that only we have certain techniques, right? And that's what we in fact would be calling them as intelligent controller. So control is critical for survival in nature, and that's how every biological creature tries to survive, and in the process takes intelligent decisions. So what can we learn from them? So that's a question. So can we learn from the intelligence that we observe in nature? And if we can learn, and based on that intelligence, if we can develop certain model, if you can develop certain strategy, right, and that if you're using for certain control application, then that is what is your intelligent control, nothing more than that. Intelligent control that way is emulation of biological control processes for solving automation problems, right? So any natural phenomenon, they're observed in biological creatures or otherwise in nature, right? Or intelligence observed in nature. And based on that, or inspired from that, you develop certain technique, and that technique, if used for control applications, then that becomes an intelligent control. Simple that, okay? Because that methodology or that technique is derived from nature, derived or is inspired by the intelligence in a biological creature or in certain natural phenomenon, and you make use of that technique, develop certain algorithm, develop certain methodology, make use of that algorithm or technique methodology onto certain control application. So you call it as a intelligent control. Okay. Intelligent control systems, as per the definition given by Technical Committee on Intelligent Control of the IEEE Control System Society. So this is how they define it, like intelligent control systems are the ones that are having an ability to emulate human capabilities such as planning, learning, and adaptation. Right? The humans, or for that matter, a lot of other biological creatures, they do adapt to situations. They do try and survive and adapt themselves to the climatic conditions wherever they are. Even if the conditions are adverse to, they still try and learn and adapt themselves. So if these kind of human capabilities or faculties can be built into certain models or systems, then that can be termed as a intelligent control. So the underlying statement is intelligent control techniques are biologically inspired to a great extent. So you talk of neural network, it's inspired by the human brain. Talk of fuzzy logic, it's inspired by the very fuzzy reasoning that we carry out in our daily life. Talk of genetic algorithm, that's again inspired by survival of the fittest. Talk of particle form optimization. Talk of any other technique. So the inspiration in a way comes from certain biological intelligence, certain intelligence observed in biological creatures. So that's why this statement, very important one, biologically inspired techniques, or nature-inspired techniques, now we call it as, in fact. Right? Okay, then intelligent control is not a single methodology. You need to understand that. It's not only the artificial neural network that you categorize as intelligent control, or maybe fuzzy logic for that matter. So it is basically a fusion of several methodologies, right? And all those methodologies, the only principle is that should have been derived, should be based on certain natural phenomena, certain intelligence there in nature, right? And today, whatever the techniques they are there, tomorrow there could be some other techniques developed, and that also could be part of these techniques. So it's a fusion of several methodologies, not a single methodology. Okay, then the main constituent methodologies that we can consider, we can think of, let's say, are fuzzy logic and neural network. Fuzzy logic takes care of imprecision. So what I mean by that is, in case you can tolerate imprecision in a solution, right? In case you can there is some imprecision, but that solution is still okay with you, fine, and that's fine. You can go in for fuzzy logic. In fact, fuzzy logic is around that only. In case you do not have a precise model available of a physical system, and when I say precise model, that means including all minute details, all physical intricacies. So how do we study in a physical system for that matter? We model the physical system into its equivalent mathematics, and that equivalent mathematics could be in terms of differential equations, or it could be in terms of integral differential equations, or maybe transfer function, or maybe state space model. So whatever is, but then from physical system you have its equivalent mathematics or equivalent mathematical model, and then you apply certain mathematical tools onto that model. There are all powerful mathematical tools available. For example, if you have a differential equation model, then there are tools to solve differential equations. In case you have a transfer function available, then there are techniques to handle transfer function, right? So there are then these mathematical tools are applied, and you analyze that system and solve that system and study that system. But then in case this precise model is not available, precise mathematical model is not available to you, then you are left with not many options. You seek the alternatives, and that is where fuzzy logic can come to your rescue. But then the solution that you obtain via fuzzy logic is not that precise, right? There is some imprecision, but then that solution works, so it's fine, right? For example, just say at times precise solutions do not work. Imprecise solutions are in fact the ones that one should go in for. Okay, for example, let's say if you are standing underneath a building, and there's a friend of yours who is at a distance from you, maybe some 10-20 meters, and suddenly there's a stone falling from the rooftop, and your friend can see that stone falling, but then since you're just underneath the building, you just cannot see that. But your friend starts telling you, okay, hey, listen, and there's a stone of this much kg falling from this much height, and it's coming with this much velocity, and it will take, let's say, this much time to fall in a head. So by the time he tells you all this precise information, so the job is done, right? Instead, workable solution could be, instead of telling all these, precise details, if your friend, just shouts out, hey, just watch out, there's a stone. Might be you'll take, certain corrective action and you're safe. So that is, a practical solution. Instead of a precise one, so imprecise will work. Anyway, we'll go further around that. The neural network is primarily based on learning, right? There's a whole lot of data available to you. That is the basic premise. That is the basic assumption. That in case you have the data available, you may not have a model available. You may not have a mathematical model available of the system, but you have the input and output pair data available. For certain kind of inputs, there are certain kinds of outputs. So that information is known to you, right? Input-output mapping, input-output pair of data. Okay, and the data might come through observations or through experiments or maybe through certain simulations, whatever, in a wherever form, but the data is available to you. Then based on the data, you can make use of neural networks, and the neural network will learn from the data, and the model in a way would be the neural network model available of that system after training and learning. Then we do have evolutionary computations, evolutionary computing algorithms. Primarily, they are used for optimization purposes, and they are heuristics in nature, and in the sense there's not much of a mathematical, background, or justification or establishment of theory behind. Yes, there is a theory it works on, but then there is certain initial population that you pick up, and then you generate another population, and then from there you reach until the stopping criterion is reached. The algorithm terminates. Either you fix up certain number of iterations, then after, or else there is certain criteria that you fix up, that okay, the value of this error may be, or whatever that objective function is or cost function is. So once that threshold value is reached, it will terminate or it will stop. So that is the evolutionary algorithms. GA is one which was almost in the beginning. Then swarm intelligence, there are a lot of algorithms around. There's just a few of them. There are otherwise, every day nowadays, there are a whole lot of evolutionary algorithms being proposed by people. So collectively, these methodologies fall under the paradigm of what is known as soft computing. So if you talk of fuzzy logic or neural network or these algorithms or some other techniques which are derived from the inspiration, that comes from nature, so they are called as soft computing techniques. So this term was coined by Lofty A. Jade, and the father of fuzzy logic. This term was coined by him in 1996. Then he said, fine, these techniques, okay, are called as soft computing. Since then, you might have you just type this word in Google, and a whole lot of literature available. Soft computing is just that, the techniques that they are there, derived from nature. Okay, soft computing, neural network and fuzzy inference system, FIS, as I've already discussed, are two of the most important consequences of soft computing. Okay, and soft computing also just mimics the intelligence found in nature. That's the fundamental principle, and there is a whole lot of intelligence available, right? If you try and observe, then based on that very intelligence, somebody comes up with certain model or certain strategy or certain technique, and that technique could be finding its applications in different domains. And initially might be fuzzy logic. If we talk of, it was used only for, the first application was for a controlling the steam engine, right there by Mamdani in 1974, the British engineer and professor and his student. So they used the fuzzy logic control for controlling the steam flow in a steam engine, and prototype steam engine there in a lab. So, but then after fuzzy logic, if you talk of today's context, then it's being used. It has been used in a lot of other application areas as well, not limited only to control, but elsewhere as well, even in non-engineering domains even. So soft computing is also the all those techniques that are based on the intelligent behavior found in nature. The basic function of human intelligence is to ensure survival in nature and not to perform precise calculation. We do not do so in our daily life. We just reason out things, and the reasoning is very fuzzy. It's nowhere kind of mathematical computations first, and then you take a decision. No, For example, in case the weather is fine and it's not sunny, that much sunny, fine. Let's go for outing. That's it, sort of that. So through soft computing, we transfer some of the human mental faculties of learning, generalizing, memorizing, and predicting into our models, or algorithms, or certain machines, and those intelligent artificial systems, in order to survive in a highly, we can develop certain machines or algorithms or control schemes that enable us to develop these complex, these simple controllers. Then I was talking, let's say, in the introduction itself, in the outline, that there are certain traits that you can associate with these techniques, or intelligent control techniques, or soft computing techniques. What are those characteristics? What are those traits? Human expertise is, let's say, number one, right? We need human expertise for some of those techniques. I mean, all these traits are not applicable anyway to all techniques, but then fine. These are some of the characteristics that these techniques, they share. Human expertise is needed, right? For example, if we talk of fuzzy logic, unless we have a human solution available, we can't think of fuzzy logic model, right? So human solution in terms of knowing the entire working of a physical system absolutely nicely, inside out, so to say, right? If you have thorough understanding about the working, then based on that very knowledge of that particular person who has that knowledge, we can capture that knowledge, and we can build a fuzzy logic model. So that's what it is. Biologically inspired computing models, these are, we've already discussed. And new optimization techniques, and otherwise you might have studied the optimization techniques, that is derivative based, gradient based, right? But then these techniques are free from that. They are heuristics in nature. They start with certain initial population, how much it should be, that's again designer's perspective. Then you iterate through generating the subsequent populations, and eventually reach out at the optimal solution. New application domains, these techniques, they're finding new application domains every other day. They're not limited only to a particular domain. So a lot of applications of these techniques you find in engineering and non-engineering. Model free learning, these techniques, in case the model is not available, the mathematical model is not available, right? Primarily, in fact, these techniques are used on those kind of situations only. If the model is available, it's wonderful. Then fine, you don't need these techniques maybe at all. But if it's partially available, or it's some vaguely available to you, or it's right, I mean, it's not available, absolutely precise model is not available, then going for these techniques. That's model free learning. You don't need a model for that purpose. Intensive computation. So these techniques, again, in the front end, it sounds very simple and straight, that there's not much of maths involved in that, but the background, obviously, yes, there are intensive computations going on. Then fault tolerance. These techniques, they are fault tolerant in the sense, let's say in a fuzzy logic model, even if certain fuzzy rule doesn't fire, you'll still keep getting certain output, although it might be a little degraded, but then the system will not collapse. Or for that matter, let's say if it's an artificial neural network, even if some neuron gets faulty, even then you'll keep getting some response from that system. It will not be crashing altogether, it will not get finished. Whereas in case of a conventional or hard computing, vis-a-vis, if this is soft computing, then the other techniques, the conventional we are used to, let's say we categorize them as hard computing. So in that, if there is some information that goes missing. For example, if you consider the case of a thermal power plant, in the control room, you get the data from the field through sensors and all, and a lot of inputs, and based on that input, on that very data, the control actions are taken in the control room. But by any chance, if some sensor gets broken in the field, and maybe you stop getting that information, however small that input might be, but then for want of that particular input, it might be that your entire system collapses. Okay, so it's that critical. Whereas these techniques, they are fault tolerant in that sense. Goal-driven characteristics. So what do I mean by this is that these, so far as you're moving towards the goal, it doesn't matter which path you're following. Right, that's what it means basically. If from place A you want to go to place B, and there could be 10 different paths. But so far as you're moving towards place B, from place A to place B, I mean, it's fine. right? That's what it is. You're not necessarily to follow a particular path. So just that, so goal driven. So far as you're moving towards the goal, perfectly okay. And that's how these techniques are. And real world applications. So these techniques, they are being used in the real life systems as well a lot. And there are a lot of industries using these. There are a lot of products, that are there in our let's say, I'll just take show you those examples where these techniques are being used in the practical real life systems. Okay, the soft computing premises, the real world is pervasively imprecise and uncertain. Precision and certainty carry a cost. Yes, obviously. The more precise you wish to go to, right, it'll come at a cost to you. It'll involve cost. Okay, and the world is pervasively imprecise and uncertain. And if you look at the real world, this is very, very imprecise. It cannot be, even if, let's say, the value of certain thing is some 10.53. Right, it can go up to 4 decimal places. Why only 5.3? I mean, there could be some other value. 5.34. You can go up to how many decimal places? So there has to be some approximation all the time we make. But then since that approximation works, it's fine with us. And uncertainty is involved. Unpredictability, uncertainty is involved in almost all the real life systems. And that's what we exploit. The guiding principle is exploit tolerance for imprecision. In case you can tolerate imprecision in your solution, it's fine. In case you cannot, don't go in for these techniques. In case you can, exploit this imprecision and tolerance for imprecision or uncertainty and partial truth to achieve tractability, robustness, and low solution cost. The cost of the solution that you achieve using these techniques is really very low. It's not that costly. Cost comes with precision. The more precise you wish to go to achieving, in the solution, the more costly your solution becomes. Okay, this is just a comparative stuff. Hard computing, soft computing. Hard computing requires a precisely stated analytical model, and no model is perfect, right? And so analytically, precisely stated analytical model, and the mathematical model, obviously, you can obtain using the first principles of that particular domain. Might be, if you talk of electrical engineering, you have your Kirchhoff's current law, maybe Kirchhoff's voltage law, or Faraday's laws, or any of the laws of electrical engineering. So making use of these first principles or physical laws, we derive the mathematical model. And but then in the process, we always have some approximations. Otherwise, if you wish to include all intricacies, all minute details, then your model might be of very high order. Let's say, if with approximations, if it's of second order, and without approximation, with all details included, it might turn out to be 10th order. And if the model becomes very complex, then it becomes really very difficult to handle that model, to solve that model. And so approximations, they are there in that. That's what it means. No model is perfect, right? There are always approximations there in the model, but then it's precise to a great extent, and it works fine. So it's absolutely okay. Soft computing is tolerant of imprecision. That's what it is. And this, you can see, often requires a lot of computation time, hard computing. And this, on the other hand, can solve real world problems in reasonably less time. And this is not suited for real world problems for which ideal model is not present. That's, in fact, the bottleneck. The hard computing techniques, in case you do not have a precise mathematical model available, then you find it absolutely difficult. You just can't handle it. Either you have some numerical techniques available or some estimation techniques. They're there, obviously. We've been handling, the systems that way. But soft computing takes care of that stuff. In case there's no model available, fine. Even then, you can handle it. And this requires full truth and can work with partial truth. Soft computing is precise and accurate, and this is little imprecise. And there's high cost involved, and there's a low cost solution. Just applications of intelligent control. Yes, I was talking about. There are a lot of applications. There's just I've picked a few to mention here. Pattern recognition, is one domain wherein these techniques have been used extensively. Then time series forecasting, where it's financial, weather, engineering, time series. So that is also where you have these techniques, finding applications in. Diagnostics, for example, in medicine or engineering, classification and clusterization of images, you could be using these techniques. And multidimensional signal processing. Right, that could be an image, that could be some speech, audio, or video, whatever it is. But then this is where also these techniques are being used. Robotics, it could be the control, navigation, coordination, robotics control, so to say. Also, these techniques find their use in. Then process control in nonlinear and multivariable control systems, you find the use of these applications. A lot of research papers, a lot of articles you can find. And just at the click of a button, if you see in the Google, you'll find whole lot of information around that. And optimization, these techniques, especially the evolutionary optimization algorithms, and they are being used for optimal optimization purposes quite a lot. Then machine vision, also for all these things, inspection and manufacturing, if at all there's some defect, etc. Right check reader, face recognition, target recognition. So these kind of applications. Also consumer electronics. Right. So there are a whole lot of products, camcorders, maybe cameras, etc. Wherein washing machines, for that matter, you find the application of these fuzzy based camcorder, fuzzy based washing machine, like that. So a lot of consumer electronics industries, they're using these techniques for decision support systems, just to help the hierarchical control decision support systems, also using these. Few examples of the use of intelligent control by the industries. So heavy industries, these are some of the industries you can search also on Google and find that are using for certain applications of theirs in Siemens, Matsushita, Stora Enso, etc. Home appliances, Canon, Sony, Gold Star, Siemens, Canon camcorder, I think I've heard of. So automobiles, these are some of the companies they're using these techniques for. And NASA for very preliminary applications, not for the precise ones, obviously no, until now. So they're also using for preliminary applications, these techniques. Why the need for intelligent control? That's what the question is. So all the real life problems, if we understand that, we can use in a way as in if the two, classification or regression. Both these classes can be reduced to multivariate function approximation problem, right? Multivariate function approximation. That is, there's and regression, in fact, is the one that we are in fact more concerned about. Say there is some, what do I mean by that is, there is some unknown nonlinear dependency between y and x, okay? Y is a function of x. And x is a high dimensional input vector, and y is a scalar, right? And the only available information is the training data set. You have this data available, xi, yi, in the product space of x close y, I is equal to 1 to whatever. So that kind of relationship is there, and so that is what you can approximate using these techniques. These real life problems that we're talking, regression or this thing classification, are large or even otherwise. You can see any real life say system. So that is large complex dynamical systems. What do we understand by large? Means it's involving many inputs and outputs, maybe, right? It's highly dimensional. Complex, the order of the system is really very high, maybe 10th order, 15th order, 5th order, 7th order, like that. And dynamical systems, obviously, there is time dependency of the response. Okay, so these kind of systems, if you talk of most of these systems, they could be having these kind of issues. Not all, maybe some of these issues. Poor understanding of the process dynamics. Maybe we do not understand the process dynamics quite well. Poorly understood dynamics. Non-availability of precise analytical model, possibly. In some of the systems, some of the cases, we do not have the model available. Ill-defined environments, and the systems might be operating in ill-defined environments, which is not very precisely defined, which is very unpredictable, right? So that is could be a case. Sufficient nonlinearity, right? They could be highly nonlinear systems, right? Or large complex dynamic systems could be having this sufficient nonlinearity. Unpredictable variation in the structure and parameter of the system, right? The system could be subjected to unpredictable variations in the very structure of the system, or there could be some parameters of the system that could change at any point in time and unpredictably, right? You don't know what kind of stochastic in nature. Okay, a bit of a change somewhere might have altogether different response. So for those kind of systems, things become difficult to handle using classical conventional solutions. When we talk of conventional solutions, so they are based on mathematical modeling and precise mathematical modeling, so to say. And mathematical model we have already discussed could be in terms of differential equations or differential equations, maybe state space transform, whatever it is. Okay, this is just to define what it is, but then you know it all these. That's what you studied. Okay. So when devising algebraic differential difference or any other kind of models from the first principles is not feasible, right? When you try to obtain the mathematical model or derive the mathematical model of a physical system, and you find it difficult using any of these techniques, so to say, then one seeks other avenues, right? And what are those other avenues? For example, neural network. Okay, in case you have a data, go in for a neural network. In case you have the human solution available, go in for fuzzy logic, so to say. So that's what. In case you find it really difficult to obtain the model, go in for these techniques. So to address the demands of highly complex and uncertain systems, soft computing techniques are used to design a new family of solutions, which have the capability of learning and adaptation to ensure that high performance can be achieved and maintained under adverse conditions even. So that's what, that is where these soft computing techniques you find them useful. Okay, let's pick up neural networks. Neural networks is what? It attempts to incorporate human brain-like abilities into artificial neural network. Okay, and by the way, we've not have until now had the artificial neural network model involving maybe not more than maybe 100, 150 neurons at the most. But then if you look at the biological neural network, and the number of neurons in a human brain, it's really very huge. That's 10 raised to the power 11. That's the number of neural networks there in human brain. The day we are able to have an artificial neural network around that number, maybe not even around, maybe much less than that as well. Possibly it will be a very intelligent machine. So, but the idea is that the human brain like capabilities, if we can build into certain network of artificial neurons, then that is what is the idea of ANN. And humans are capable of analyzing ocean of data obtained by various sensors and routinely solving complex problems of decision making. At any point in time, let's say, if we at this moment itself, you're listening to my talk, might be you are busy thinking something else as well. At the same time, you could be writing few things. We do our things on a computer. We listen to our music and we still keep typing things, and maybe we can do some other task as well. So multitasking or analyzing the ocean of data at the same time, that's what a human being is capable of. So likewise, in case you have an artificial neural network of reasonably large number of neurons, then that also could be able to handle large data. Very difficult to replicate the human information processing abilities in smart machines, right? It's just not been possible until now. May not be in the near future also, that you can have those many neurons in this network. So just difficult to replicate the entire human and the thing. Okay, neural network is a black box approach. So what do I mean by that? That what is there, let's say there is a system in the black box, but you do not know what the system is about, what the system is. The only information available to you is the input X and the corresponding output O. Right, that's the only information available to you. Input-output mapping. For input and these kind of inputs, you have this kind of output. That's only information, nothing about the systems. That's how it is called as a black box approach. No previous knowledge, but there are measurements, observations, records, also to say the data pairs. So that input-output data pair is available to you, right? That is known to you. And behind neural network stands the idea of learning from training data. And in case the data is available, there's no model available, you do not have the information about, doesn't matter. Based on that very data, train that artificial neural network, and that very neural network will start, behaving as that particular system. It will be able to, give you a response the way you like it, the way you trained it. So it's a black box approach from that point of view. Fuzzy inference system we talk of, And so fuzzy logic, as it's written, arose from the desire to emulate human thought processes that are imprecise, uncertain, and usually expressed in linguistic terms. So, for example, in case you want to say from your place you want to go to some other place, for example, from Kurukshetra to Delhi, the distance is around say 160 kilometers. Okay, so if somebody just wants to estimate how long it will take one to go to Delhi from Kurukshetra, and if I ask, let's say, how far is Delhi from this place, somebody tells me around 160 kilometers. That around 160 kilometers serves the purpose, I'll be able to kind of estimate, okay, if it's around 160, fine, it'll take me something around 3 hours. That's okay, and that's what my purpose was, right? He or she telling me might not be that precise, that it's 158 kilometers and this much meter and this much centimeters, this much millimeters, like that, right? So at times, you don't require the precise solutions, and in case you have the tolerance for, that's what fuzzy is about, then go in for fuzzy logic. Okay. So, it's around the human thought processes. It's around the fuzzy reasoning that we carry out in our daily life every day. So, it's the name is fuzzy because of that reason. So, a necessary condition for a fuzzy logic solution is the existence of human solution to the problem. If there's no human solution, there'll be no knowledge to the model, and consequently, no sense in applying fuzzy logic. Right? In case you do not have a thorough understanding of that physical system, right? There's no point of using fuzzy logic model. You cannot develop, in fact. Fuzzy logic model is just kind of then statements only. If this is the kind of situation, then what is the kind of action you take? Right. So that very knowledge, that comes from that expert only. You try and capture that knowledge by interviewing that expert, and try and develop the model around that, and develop certain fuzzy logic rules, maybe 10, 20, 50, whatever it is. So these rules are nothing but the very knowledge that you have about that system. And in case you do not have that knowledge, you cannot have the rules, cannot develop the rules, and you cannot have a fuzzy logic. Okay. So existence of human knowledge, human solution is not sufficient though, right? It is required, it's a mandatory thing, but then that's not sufficient, right? You have other things as well. So the basic requirement for fuzzy inference system is one, human knowledge is available, mathematical model is unknown or impossible to obtain. Right. So you do not have a model available, or it's just next to impossible to obtain that. Fine, going for fuzzy logic. The process is substantially nonlinear, and there is lack of precise information. So if we have such kind of information, such kind of situation, then you can use fuzzy logic. Possible difficulties. Fuzzy inference system. When you wish to develop a fuzzy model, then there are difficulties. The first and foremost is knowledge is very subjective, because the very basis, the very foundation is the human knowledge available, and it's very subjective. Let's say if you obviously try and capture the knowledge by way of interviewing that fellow, by putting maybe some 10, 20 questions. So if you put, let's say, 10 questions to the expert A, and that expert A tells you 10 responses. If you put the same 10 questions, set of 10 questions to some expert B, then for sure the expert B will not be telling you the response is exactly the same that they were told by the expert A. So it's subjectivity is involved in that, So that's a problem. For high dimensional inputs, the increase in the required number of rules is exponential. As the number of input goes up, then the number of rules required would also go up really, really very heavily. So the exponential rise in the number of rules, that in a way, more the number of rules, so the complex the system becomes. Okay. Knowledge must be structured, but experts bounce between a few extreme poles. Trouble structuring the knowledge, too aware of their expertise, tend to hide knowledge. There's some of the issues involved in that, right? The experts bounce between a few extreme poles. Somebody, some expert says the answer to, for example, to a certain question that it's a daytime. Somebody to the same question says it's a nighttime, altogether different, so to say. That's what it is. So at times you find it difficult to structure that knowledge, capture, and then you make use of it. Fuzzy logic models, they are white box approach. Just like neural network had black box, this is white box. That's because we should be knowing inside out. We should be knowing, full working of the system thoroughly well. That's why it is a white box approach. We should be able to see through that system what it is and how it works, and under different situations, different inputs and all. So that's why it is, a white box approach, so to say. Structured knowledge right? Could come through experience, expertise, or heuristics. No data required. If then rules are the most typical examples of structured knowledge. If then rules, that's what I was talking. If, let's say, if the weather is comfortable, let's go for walking. If the tomato is red, then it is right. So to say, these kind of rules, if the speed is high and is then apply very hard brakes. If the error is small, then increase the gain a bit, like that. Okay, so then some knowledge plus some data, it's a gray box approach, right? I mean, you have the knowledge also about the system, may not be thoroughly well, but the data is also available. So then you make use of what is known as a combined or synergetic use of these techniques, and that is what is the neurofuzzy models or neurofuzzy systems. Gray box situations are under this paradigm of hybrid neurofuzzy models. You have the data, you have the knowledge, but not complete in itself, then gray box approach. Okay. Advantage of neural network models, it's a property of learning from data. In case the data is there, perfectly fine. You can do without model. You can approximate any multivariate nonlinear function. Do not require deep understanding of the process. Robustness against noisy data at times. Inherent parallelism. There is parallelism. Even if some neuron gets faulty and gets broken, then also it will keep working. Advantage of fuzzy logic, we've already discussed. I mean, non-linear systems or model is not available, or it's highly uncertain environments, so things like that. You could be using fuzzy logic models. Okay. Disadvantage of neural network, yes, long training or learning time. So it takes a hell lot of time to train a neural network. So that's where the bottleneck is, and then the problem with local minima at times gets stuck up there in that. Do not uncover the underlying process phenomena. How the weights are being adjusted, although there are algorithms. But then what you get to know is at the end of the training only. These are the final weights. So underlying process at times is not uncovered. Prone to poor generalization or overfitting. At times you train the neural network to the extent that it's kind of becomes a memory chip. For all possible or conceivable conditions, you train it, and that in a way, is not the one that is the aim. A little or no guidance about optimal initialization, structure, or type of neural network. Until now, even there's not an established theory that this is the initial weights that you should be assigning to, and this is the kind of structure topology that you should be using for this kind of applications, for these kind of category of applications. Which type of neural network you should be using? So that's it's up to the designer. So designer's perspective says it all. Neural networks paradigm relies heavily on training data that may be expensive or unreliable at times, because the very, very fundamental requirement here is the data. And if the very data is corrupt, if the very data is not reliable, right, then the solution that you'll be obtaining using that neural network will not be obviously the one that good ones, obviously they'll not be. Okay. Disadvantage of use of fuzzy logic models. Human solution to the problem must exist. If it doesn't, no point. And the experts, obviously, I think we've discussed this, I don't know, may have problems structuring the knowledge. With the number of inputs rising, the exponential increase in number of rules, that is the curse of dimensionality. And learning the membership function parameters. We have the parameterized membership functions. A lot of them, triangle, trapezoidal, Gaussian, bell, etc., etc. And all these membership functions, they are expressed in terms of certain parameters. And so, what are the best possible values of those parameters? What should be the shape of those membership functions? So that also at times become difficult to learn the membership function parameters to obtain the optimal ones. Z is, I think, is a very old, very almost initial optimization algorithm that is based on the mechanics of natural selection and natural genetics. There are certain, that's the idea behind is survival of the fittest theory given by Darwin. And there are certain operations involved in that. You need to encode the chromosome string. That's the initial solution, so to say. One chromosome string is one solution. Defining the fitness function against which you will evaluate these solutions. Then initialization of population to begin with, how many solutions to pick up. then selection of the qualified chromosomes to mate and then generate another population. Then these are the operators, crossover and mutation, right, used in the process, and then you iterate until there's a stopping criterion. So that's the whole thing. I think we can skip this because now we have all other algorithms also available. Then synergetic use of intelligent control techniques. So that's also the way forward. And these techniques, in fact, they are not in competition with each other. That fuzzy logic is in competition with neural network, and neural network is in competition with fuzzy logic. No, they are complementary in nature. So there could be the weaknesses of each of these individual techniques, but then can we think of combining two techniques wherein the complementary strengths of each other can be used, then you can have an improved or a better result or better response. So people are doing research around that synergetic or combined use of these techniques, and that's what it is. And using these techniques, a lot of intelligent control algorithms or controllers have been designed. Okay, so this area is being pursued actively both on academic as well as in industrial fronts. And as I said, the techniques are complementary in nature rather than competitive. Okay, if you go by the factual information, that's what I was saying. Might be in just you Google something around fuzzy logic or intelligent, this control or maybe neural network, you'll find a lot of information. And if you go by the statistics of patents being filed and issued in this area, or papers being published, or application different domains, and the journals being published also in the area. So what you can say that in a nutshell, that the future applications of intelligent control are likely to evolve around a synergetic approach. Okay, intelligent control, that's an important statement, is not a closed and clearly defined discipline at present, right? It's open to any technique and every technique that gets developed tomorrow, for example, but then that's based on some intelligence there in nature, so that can very well be part of intelligent control. That's what it means. It's still open to that. I think this is what we've already discussed. Concern in control problems is with regression primarily. When and where to use fuzzy logic, I think that's also discussed. Okay, when and where to apply neural network. The less previous knowledge exists, the more likely it is that neural network, not fuzzy logic, will be used. Okay, this is an important statement. Maybe you can go through yourself. Whenever there is an analytical closed form model using a reasonable number of equations that can solve the given problem in a reasonable time, at a reasonable cost, and with reasonable accuracy, there is no need to resort to intelligent control, right? In case you have the mathematical model available to you, precise model available to you, and that too using a reasonable number of equations. The model shouldn't be very complex or very high order, involving a lot of equations. And with using that model, if you can solve the problem in a reasonable time, the time taken to solve should not also be really very large, and at a reasonable cost. Solution should be coming to you at a reasonable cost and with reasonable accuracy. And all these parameters are met. Absolutely no need to use intelligent control techniques. It's simple and straight. But then, unfortunately, intelligent control, you find some situations wherein at least one of these criteria is not met. Maybe either you have a model available, fine, with a reasonable number of equations, but then the time it takes to solve is really very large, or time also if it takes little less, okay, but then the cost involved comes out to be really very high, or the solution may not be that accurate. So some of these criteria not being met, then intelligent control comes to the rescue, right? But otherwise, if that is the situation, do not use intelligent control, right? Okay, so quickly, this is just to share with you the fuzzy-based intelligent frequency control strategy in a standalone hybrid AC microgrid. The work of one of my student, right? We picked up. You all understand what is a microgrid. By now, and this is where we have at the customer's side, or so to say, at the distribution level, we have these smaller generating units. We do have the associated energy storage devices. Obviously, they're required because of the intermittence involved in the renewable sources, and primarily we do have the renewable sources only. And so these smaller generating units, right, in terms of or hundreds of kilowatts, integrated with power grid in the form of distributed generation. right? You could be using the microgrid in islanding mode or grid connected mode, depending on. And the penetration, I mean, the constituents of the microgrid primarily are, these renewable sources. We can have wind turbines, we can have photovoltaics, we can have fuel cells, micro turbine, diesel engine generator, batteries, etc. So this is the structure of a typical microgrid. That's, we have the main grid, we have these, these renewable energy sources or storage devices coupled through the local controller, and all in all up to the microgrid central controller, right? There's a point of common coupling, static switch, and all. So I think this detail is understood by you. Then the idea was, how do we regulate the frequency in case certain, operating conditions are changing, varying, right? And frequency obviously fluctuates unless if you have a balance is maintained at all the time between generation and consumption, is perfectly okay. 100 megawatt or 100 kilowatt is being generated and 100 kilowatt is being consumed. There's a balance, so the frequency is there, constant. But this balance obviously doesn't remain. Every time there's some load being switched on or switched off, so that keeps on going. So that's why we have the frequency imbalance and frequency deviation from the standard frequency, and this mismatch can be regulated by using certain controllers. And this case study, I think, investigates that we have investigated is around using these wind turbine, PV panel, fuel cell, DC, and battery energy storage system. And mode of operation we picked up was islanded mode, and disturbances we considered were load variation. We varied the load, and then power mismatches due to changing environmental conditions. We varied the wind speed, and we varied the solar radiation levels. And with the variation in wind speed, obviously the power output from the wind turbine would be different. With the variation in solar radiation levels, the power output from the PV panel would be different. So this is a variation, this is a variation, and a load variation. So these are the disturbances that we considered, and it was islanded mode of operation. And these were the components, or so to say, subsystems that were there in that AC microgrid. Okay, this is what the structure was. WTZ, fuel cell, PV, diesel engine generator. That is where the controller we applied, and battery energy storage system. This was the main load, PL1 and PL2, and okay, these were the secondary loads. Okay, and these were the values that we considered for these units. In total, the load of main load was 300 kilowatt, and the secondary loads were 30. In total, together, these are the ratings of these components. Conventional controller, we all understand PID controller, that's the equation. And these are the gains that we obtained. But then we know the technique we used was fuzzy gain schedule PID controller. We tuned the PID controller. We scheduled the gains of PID controller based on the fuzzy logic, right? And this is the schematic that indicates that using a fuzzy logic model, we tried and scheduled the gains, or so to say, decided the gains of this particular plant. And these are some of the the membership functions for input variables, triangular membership functions. But then that's what I was talking. Might be this is a symmetrical shape. It may not be symmetrical, and this may not be optimal in case you use certain optimal algorithm onto that. So the shape could be altogether different. I mean, it will have to be triangle, but then it could be having certain different angles. Then the output variables membership function we considered around that. And this was the fuzzy rules that we set up for this particular problem. This was the simulation circuit we implemented, obviously, onto MATLAB. Simulation results under various operating conditions, and that is the variation of solar irradiance, wind speed, load. Under normal operating condition, main load was 300 kilowatt, solar irradiance was 800 watt meter per square, wind speed was considered as 12 meter per second under normal operating condition. And how the output power characteristics for PV cell and wind turbine. PV cell with solar radiation, with the variation of solar radiation, and how the power varies of PV cell. This is what the curve for. And likewise, with wind speed variation, how the power output varies. This is what the variation was. And we considered this variation in the output power characteristics when we vary the solar radiation level. It was 600, so this was the power. Then it was made 1,800 like that. This was the variation from 0 to 4 seconds, 4 to 6.5, 6.5 to 17 seconds. Likewise, this is a variation in wind speed we considered 0 to 8.5 and 10.5 with this. Okay, And this was the load variation we picked up to maybe 12, 12.5, 0 to 12.5. It was 300 all, then 12.5. Suddenly, the 30 kilowatt was injected into. Then it was removed also. Okay. And then this is frequency versus time characteristics, like the frequency deviations versus time. And this is using PID controller, the blue color, and this red color indicates the fuzzy gain schedule PID. This was look at this. This is simply without fuzzy gain schedule is less oscillatory and also settles down faster. So this is just the observation. Like change in frequency versus time, again, so this is also indicating that it's a little better than your conventional PID controller. Okay, so that's what this observation was. Then final concluding remarks. In the recent years, obviously, intelligent control you find is emerging and is finding a lot of applications, and it's being actively pursued also by the academia, as a research. Okay, and prominent intelligent control techniques we've discussed, fuzzy neural network, but there could be other techniques as well. And complementary use of these techniques is finding various applications. Okay, and the use of fuzzy logic neural networks for application in many different areas. That is also the case. Or for optimization purposes, we have evolution algorithms. A lot of them, weight optimization, maybe multiverse optimization, differential, evolutionary algorithms like that. And there are neurofuzzy approaches, genetic fuzzy approaches, or even neurofuzzy genetic, or all these kind of combined approaches. Okay, and they're being used by for a lot of applications. That's right. And yes, the application domain is expanding, beyond engineering. Okay, and the circle of intelligent control techniques will widen beyond its current constituents. That is what is expected. So fine. With that, I thought I should leave you on a smiling note. That's why this particular flower onto that. So with that, thank you so very much. Thought of giving you the flavor of intelligent control and what and what, why and where all it can be used. That was the idea. So I intentionally kept it simple and not too much into complex research domain. I hope and believe that you might have got something out of it. If you got it, it's wonderful. So thank you so much. By any chance, you couldn't make out, you won't have any takeaways. I don't know. Maybe I'm sorry for that, but try to give you a flavor of this technique. So with that, I close my session. In case you have any questions or queries, you're most welcome. I'll try and respond to that. Thank you.
Thank you, sir.
Yes, please.
Thank you, sir, for the wonderful session, sir. Participants have questions. I have put in the chat box, sir.
Okay, let me come to that. Okay, now I'm there with you. Let me scan through the chat box. Okay. How to know which intelligent control method should be used for controller? All right. So that depends. Like in case you have the information available about the working. Right. In case you have good enough information about the working of a system, fine, going for fuzzy logic. Or else you do not have much understanding, but then you have the data somehow, through some observations or through certain simulation of certain formula somewhere, or maybe from certain records or from some experiments. If the data is available, going for neural network. So just that. So you could be using any of these controllers depending on the information that you have about the system available. And this was a question from Prerna Mohapatra. I hope, Prerna, you used an answer. How you selected KPKIKD for your proposed microgrid controller? Yeah, that was, yes, there's a question from Devi Karani. So this was the fuzzy rule based, if the error, so we picked up error and derivative of error. If the error is small, for example, and the rate of change of error is also small, then the gain should be high or low. That's what we understand, how it should be. So depending on that, we formulated this rule base. There was this table, that you might have seen. So, so we developed the fuzzy logic rule base for the situation, all different situations. error, and we picked up, let's say we divided this error into 5 different linguistic terms. Negative large, negative, medium, maybe then zero, then positive small, positive large. I don't remember, but you can divide the linguistic variable into whatever the number of linguistic terms or linguistic values, and based on that, obviously you'll be having these rules based, right? So, and then how many linguistic terms you should have also depends. For example, you have temperature as a linguistic variable. It could be low, medium, and high, or it could be very low, low, medium, high, very high. Instead of 3, you can have 5. Instead of 5, you can have 7. Like, but then how many? There has to be a trade-off, right? If there is not much of an improvement by way of increasing the number of linguistic terms, because every increase in linguistic term will make the system little more complex, will involve a lot of more number of fuzzy rules, and obviously every linguistic term has to be represented by a fuzzy set. So this we'll have to see what is the appropriate number that you should pick up, and in terms of those very linguistic terms, you devise these fuzzy rule base, and instead of tuning these KPKID, otherwise we tuned using this kind of a fuzzy that if the error is small and rate of change of error is large, then the gain should be medium or high or a low, like that. Okay, and what are the okay? There's another question from J. Surya Prabha, research scholar. Fine. So, what are the possible challenges in implementing intelligent control in comparison to conventional PI control in renewable energy commercial integrated connected systems? So, see, the possible challenges could be coming from maybe in case you have in the first place. So these systems, there's nonlinearity involved in. Like you could be using even for with every renewable energy source, there has to be a control unit. Let's say if you have a PV inverter control, right? Then you have wind turbine. So with each unit, there is a controller associated. And how do you control? You have this VDC link available. So what is the voltage level there? And you monitor that and you apply and make a comparison. Certain current variables are picked up. I think you are working this area, you might be knowing. So that information, if at all, is available nicely to you, even without a model of that particular system, fine, you could be using any of these techniques. There's no challenge as such, right? So far as you have the information about either the working of it or else the data, two things are required, in fact. In case you do not have any of these two, but if you have a model available, you can nicely model it using certain mathematics. Fine, don't use these techniques at all. And the last question, I think, any intelligent controller application for harmonic reduction in power quality. Power quality, yes, harmonics is a major issue. No specific, even for that matter, a simple PI controller can work there, and it has been work. It's there in use. But then you can schedule the gain of a PID controller using maybe fuzzy, or I think I've not, to be honest, used any intelligent control into power quality harmonics. I've used it for frequency regulation. That's where I find these very, very useful, and results are also really very good. But you can try these combinations in case you have difficulties otherwise in conventional solutions by way of the model not being available or by way of some other issues. But then these solutions are cheaper and workable, and at times useful and better than, right? And maybe the only alternative. So thank you. Yes, please. Yes, Jivan.
Thank you, sir. Thank you for giving us your valuable time, sir.
Thank you so much, and it was nice to meet you. I thought the participants, their time was worth, being there in the session. Thank you so much.
Thank you, sir. It was a wonderful session, sir. We will be in touch with you, sir.
Okay, sir. Yes, all the very best, and you're doing wonderful. So I'm sure all participants at the end of this 5 or 6 days course will definitely have some takeaways from each of these sessions, and that they can make use of. They can pick up the thread out of every discussion, and maybe can use in their academics or research. That's what the aim is. Thank you. Thank you.
Thank you, sir. Thank you so much, sir. Okay, dear participants, now we will move to the next session of the day 2. So it is at 11:45. So you, at the meantime, you can fill the feedback and attendance form. Okay, so attendance form will be open up to 11:30. It is already shared on YouTube. Okay, and we will meet you again 11:45. Okay, we are here. Keep on track with us, and thank you for attending this session, the first session of the day.
Jeevan, can you hear when I am speaking something? Still connected only, na? Hello, hello, hello. Good morning, sir. I think background sound is coming.
Yeah, Dr. Asha, I am audible, right?
Yes, sir, you're audible.
Okay, okay. Thank you. Good
Can we
morning.
start, sir?
No. You can start by your time. No problem. Just I verify that whether everything is fine or not. Okay.
Yeah, it's
Fine.
11:45, sir. Even we can start now also. I'll give an introduction about.
No. You can start.
Okay. Good morning, sir.
Good morning.
Yeah. And good morning, dear participants. Now we are entering the second session of the second day of 1 week STTP. And now we have the expert from NIT Tiruchirappalli, Dr. G. Sharavanilango sir with us, who is handling this session on effect of partial shading and interconnection schemes for PV system. Hearty welcome, sir. It's my privilege and honor to introduce Dr. G. Sharavanilango sir, Associate Professor, Department of Electrical and Electronics Engineering, Department of Electrical and Electronics Engineering, NIT Trichy, in this 1 week STTP, who is also serving as a visiting professor in North Carolina State University, USA. Dr. G.S. Ilango received his PhD degree from NIT Trichy in 2009, and he is a postdoctoral fellow at Department of Electrical and Computer Engineering, North Carolina State University, USA. He has 16 years of teaching experience and served in different administrative capabilities, including Associate Dean P&D of NIT Trichy, member of different quality assurance committees, BOS member and selection committee member of many institutions. He has more than 94 publications in his account, which include 50 publications in international journals of IEEE transactions on industrial electronics, power electronics, energy conversion, sustainable energy, IEEE Journal of Photovoltaics, IEEE Journal of Emerging and Selected Topics in Power Electronics, etc. Of which few are in IEEE Power Electronics, electric power applications, LCV renewable energy, energy conversion management, electrical power and energy systems, etc. And more than 40 plus international conference publications are there in his account. And he has conducted several JN courses and he has bagged several awards, which include Bhaskara Advanced Solar Energy Fellowship from DST, Indo-US Science and Technology Forum in 2017, Young Faculty Research Fellowship from DIT in 2017, Young Scientist Award for Fast Track Project from DST in 2009, received first Innovative and Inspired Award from Caterpillar Electronics in 2013, And he has completed more than 5 sponsored projects and worth several crores under DST, BHEL, NLC, DIT, etc. and has 4 ongoing projects under Ministry of Coal, Government of India, worth 1.8 crores, SERP, DST, and from DIT Vishwesvaraya Young Research Fellowship Scheme. Under his eminent guidance, he has more than 7 students completed PhD and more than 6 scholars are pursuing PhD now. From the past 12 years, he is working in the area of renewable energy system and has versatile knowledge related to solar photovoltaic systems and wind energy conversion system. And he has developed several impressive methods like Sudoku PV, array configuration, partial shading and fault detection, methods and control techniques for DC nanogrids. Moreover, he has developed grid integration techniques for solar PV and wind power generation systems, developed energy efficient matrix converters, developed industry standard interleave 250 watt DC-DC converters, laboratory prototype UPFC, and developed the system for electronification of groundwater control and conveyor system for mines, dynamic loading for mines, DEG system for boiler flue ducts. And his area of interest include power electronic controllers, FACS controllers, photovoltaic system design, and wind energy conversion system. And he's a senior member of IEEE, and he has 2 granted patents in his account and 3 applied patents. He is a renowned academician and researcher who has provided many significant contributions in the area of solar PV systems and wind energy conversion systems. Hearty welcome, sir, once again. Now I request Professor Dr. Sharavana Langosa to start the session.
Okay, so thank you, Asa, for your very long introduction about me. Okay, so I'll start. I'll straight away go to my lecture. So
yes, sir.
Thank you for giving me an opportunity to deliver my lecture to the very large crowd of participants. So as I heard from you, so
yes,
first of all, I thank you and your members of the coordinating committee for giving me such an opportunity. So a very good morning to all the participants. Okay, so I hope that all are safe and healthy and safe in this COVID-19 situation. I hope that we join together to actually we all have one thing in our mind, that we actually has to learn. So that's a very important aspect. Though there was the situation was very bad, we are joined together to learn a few things about solar PV. So greetings to all. So who are within as a participant for this this particular course. So basically,
sir, Ilango sir.
Yeah.
Sir, you can share the PPT also.
Yeah, I'm sharing it.
Yes, sir.
Okay, so the content, what actually I'm going to take today was, effect of partial shading and interconnection schemes for PV system. So it means that, what will be the problem if there are partial shading, and how actually we can mitigate the effect of partial shading in a PV system. So these are the 2 broad ideas which I have taken today for this particular course. Okay, so getting insight to that, so this is my brief overview of what actually I am going to talk today. So introduction, so what will be the mismatch if there are series connected PV modules? What will be the effect of such partial shadings on a PV output power? What is the significance of bypass diode? We will see why a bypass diode is needed, and a few interconnection schemes which actually we have developed to mitigate those problems. So these are the broad contents which actually we are going to learn today, maybe by this hour. Okay, so like the simple introduction about PV system, and this is not new to you. I hope you also know that the PV systems are increasingly popular. So maybe due to reduced cost day by day, there are some attractive government subsidies which are coming. So that may be another one reason, and there are green policy mandates. So such as that we want to reduce the carbon dioxide emission. So we actually want to move towards renewable energy. That's one of the thing. And the another problem is the fossil fuels are getting reduced. So we are actually scientists and everyone is actually seeking an alternative. So those alternatives are moving us to go to PV system. And coming on to the PV system, there are 2 things. One is the big plant, And another thing is a rooftop PV plants actually, which everyone can actually use it. So grid-connected rooftop PV plants are installed in urban and suburban areas. So there are a lot of PV such plants are coming. We'll be able to see, and many governments are actually having a plans to actually have a PV plant in every house. So that's the order of the day, which will be coming tomorrow. And ideally, what we feel is that PV arrays should be installed in a shade-free location. That's what actually we try to do it when we are installing it. So when installing it, we will take all the measures in such a way that the PV array will be installed in a place where there is no shade. That's what our motive. But then what will happen, we will actually see in the course of the lecture. Okay, so to understand how does this PV array behaves, we actually have to start up with what? The characteristics of a PV model. So how does the PV characteristics of a PV model looks like? Okay, so just I hope that everyone would have known it, but then just for a brief overview, actually I'm taking. So this is actually the IV characteristics of any PV model. Actually, a PV model which has been given 250 watts. So there is a 250 watts peak. Keep in mind that in all other electrical appliances we have only watts, but in PV alone we will have the power rating will be given in watt peak actually. So what does it mean? That this PV panel can give you a power of 250 watts when actually the irradiation was 1000 watt per meter square and the temperature was 25 degrees Celsius. So these are the two important points which we have to keep in our mind, that these particular characteristics is only when if you maintain two things, that is like two parameters, that irradiation is at 1000 watt per meter square and the temperature of the PV panel is 25 degrees Celsius. And so this PV model, the PV model will be actually connected to a master. So we will say there is a DC-DC converter will be here. Okay, some DC-DC converter. So DC-DC converter will be there, and which we will actually call as a MPPT. That's a master which will control it. Okay, what does it mean? Yeah, of course, the PV has a whole characteristics, but this MPPT controller will try to operate, always try to operate at this particular point, where there is the operating point is called as DFDP and IMPP. So that's the job of an MPPT controller. So it will actually try to maximize or try to operate at that particular operating point by changing its duty cycle. Okay, but that particular portion is not in our control, so it will give a suitable D in such a way that this particular thing will operate at this MPPT. So this is the point where the MPPT will try to operate it. And there are various operating points. This is the open circuit voltage where the current is 0, and this is the short circuit point where if it gets shorted, and whatever may be the case, these are the various characteristics of the PV model actually. So now, how does it changes? Is these particular characteristics is fixed or not? Is these characteristics? Because we should understand the characteristics of the PV model. So before we are going to say that. So whether is these characteristics is fixed or someone can change the characteristics of the PV model. So who are the two parameters which can actually change the characteristics of the PV model are? They are what? They are irradiation and temperature. And this irradiation and temperature depends on the nature. So a PV has a characteristics. A PV model has a IV and a PV characteristics, but it depends on two parameters. They are irradiation and temperature. So what you understand from here is the characteristics of the PV module is a flexible thing or is a function of irradiation and temperature. So that's we have to keep in our mind. We will see that how actually the characteristics will actually differ. How does it differ? So you see here, it's effect of irradiation on the PV characteristics. So if how does it change? You can able to see that the shape of the characteristics is similar. We are not able to observe any difference in the shape of the curve, but you can see the parameters as affected. So whenever the irradiation was changed from 1000 watt per meter squared to 400 watt per meter squared, you would be able to see there is a large change in the short circuit current. You see the short circuit current has changed a lot. It is about 8.64 here. So it is 8.64 here, whereas it moved here up to F1 maybe more than 5. Okay, when it is actually what 600 watt per meter squared, 400 it is still low. So we'll be able to see the current actually is actually a function of irradiation. And you can also see from the PV curve that the power actually changes very largely. So you can see this is a maximum power around 250 watts. When it came to a power of 150 watts at 600 watt per meter squared and from 400. But what's the thing we observe here? What's the unique nature between the earlier one and this is the shape remains same. There is no change. There is no alter as can happen in the shape of the PV characteristics when the temperature and when the irradiation changes. Okay, so that's one thing we observe. And next thing is when I move on. So when I move on, so what will be the case? What will be the case when the temperature when the temperature actually changes? What will happen on the PV characteristics? Okay, so when the temperature also changes, we would be able to see that the power changes. And what's the observation? When the temperature increases, power falls. So power is reducing. Okay, and here also there is no much change in ISC, but there is a small change. There is a small change in ISC, but that change is not that much. But then we would be able to see a small change which is happening at VOC end. So VOC end there was a small change, and then there's a VMBP point. There was a change. But again, the unique point is similar. That means there is no change in the shape due to the effect of the temperature. The shape has not changed. The shape still remains, but only the operating point actually has shifted or left or right depending upon the parameters of the PV. So that's what we observe. Okay, right? So now we are very clear that we know the characteristics of the PV module. So that is known to me. But then the question comes to me that whether I need only one module is enough for me, and you know that the rating of the PV module which we have seen is 250 watts. But in case, if you take a typical home or a house, the load will be at least a 1 kilowatt. How do I cater? Or how do I feed with this 250 watts panel? I hope that you can understand that when you are actually so what's the simple logic we'll try to use is we'll try to connect them in series to increase my voltage level. We may connect it in parallel to come to the required current rating. So what we really understand is we understand the characteristics of the PV module, and this one particular module is sufficient enough only to cater a 250 watts. But to have a more rating, to increase the rating of the voltage, we have to go for a series connections of the PV module. And to increase the rating of the current required by the load, we will go for parallel operation of the PV module. That's what the understanding was. And that's the big flexibility of PV panels. See here, we started with cells. This is a very simple cell. And cells are connected in series. All the cells are connected in series in a module to become a module actually. Okay. So then the module will be connected in series, and they are called strings actually. Okay, so the modules are connected in series to become strings, and then actually, so this depends on what voltage rating you need and what current rating we need. But surely we have to go for a series connection and a parallel connections. And the next is array. So we will call this an array. So when you look into an array, we need a series connection and we need a parallel connection. Okay. So we first understand how does the characteristics of the PV will be. And later we seen that how does these characteristics changes with temperature and irradiation. And now what actually we are trying to do is we are trying to connect them in series and parallel. So the thought which is coming in our mind is when I connect them in series, actually whether the characteristics will be differing or whether they will change or not. So when you understand how to draw the characteristics for a two series connected string or two series connected module, then we will be able to understand that what actually will be the effect of some partial shadings or whatever may be. Okay, so we understand that we have to connect modules in a series and parallel. So now we will look into the aspect of if I connect two modules in series, how does the characteristics looks? So how does the characteristics looks? So and so before that, this is a very important point. Why actually PV differs from all other renewable energy? PV is the one renewable energy source which actually can provide power from milliwatts to several megawatts. You can able to see a PV in a calculator. We can also see a PV in a power plant which is creating megawatts. It was a very, very unique nature of the PV actually, not for the other renewable energy sources, which makes this PV very popular throughout in every sphere of our place. Okay. So now getting inside to this, how do I draw IV curves of a string actually? So when I come for an IV curve of a string, so two modules are connected in series. Okay, so two modules are connected in series. I know this is actually the characteristics of an individual module. These are characteristics of the individual module. These are characteristics of the individual module. But I want to know how do I draw the characteristics of the series connected module. So how do my V string versus I string looks like? Okay, so V string versus I string looks like. Okay, so the assumption which I made is the two persons which we have tied together, or the two modules which we have tied together, has similar characteristics. That means the module 1. This is the module 1. So this is module 1, and this is module 2. The assumption what we have made is module 1 has a similar characteristics as module 2. So that's what understanding. So if they have the similar characteristics, if module 1 and module 2 has a similar characteristics, then it is easy for us to draw. And in a series connection, we know that I module 1 should, or IPV1 should be equal to IPV2. Okay, that's must. So as per Kirchhoff's current law, Kirchhoff's voltage law, that the resistance, the current in a series string has to be same actually. So now if I want to draw the curve, PV curve of a string, you can find out from here. This is a current 0. So for a current 0, we can add 2 PV1. So what is VPV1? So VPV1 is almost 39.8. 84 or something like this. So we can add it and draw a point here. So similarly, for a 1 ampere, you mark here, double it and draw this. Similarly, you draw different curves, different points. So we can make different points and we can actually complete the curve. So it's very simple. And we now understand that we know how to draw the IV curve of a PV string. It's just an addition of voltage. Current remains same. The current remains same and the voltage is added. So that's what the characteristics of a PV strings looks like when they are connected in series. So it's very similar when they are connected in parallel actually. So when they are connected in parallel, it's voltage problem. So when the voltage is same, so you go from this voltage and try to add the current. You will get a good VI curve of the string. Okay, so you can actually add the current. So it is additive in nature. So you can add the current in all the points. So you mark a point here like this, and then you try to draw the IV curve of a string. And similar is the case if there was an array. Similar is the case if it is an array. So the voltage is added here. The voltage is added in this particular point, while the current is doubled. Okay, it's fine. We have actually seen how the IV curves of a series connected modules and parallel connected modules and series parallel connected modules. All are fine. But what's observation out of it? What's observation we got out of it? So that's actually very important. The observation is still the IV curve, the shape of the IV curve has not changed at all. There is no change in the IV curve shape actually. The shape is actually same. But now, what is our assumption to draw this particular IV curve? The assumption which we have taken to draw this IV curve of a string is all the modules are having same characteristics. So all the modules have same characteristics. But in the real field, but it's in the real practical place, we have to ask the question ourselves whether the characteristics of the PV module which are connected in series will really have the same characteristics or not. Is there any possibility that the characteristics can differ? If there is any practical constraints which will make the characteristics of the modules difference? That's a question which actually we put forth in work with us. In that particular scenario, how does the IV curves of the PV array looks? Or now, what are the possible modes, or when they will actually differ? That actually you can think in your mind and see. So what are the, or at what place they will differ actually? Okay, so what are the places where actually they can differ? So they can differ if there is any cell processing problem, a difference in cell processing. That's a practical point. That's one of the places where actually we can try to have different cell processing. But its effect, the effect of cell processing on a PV characteristic or a change in current due to the cell processing is very, very, very minor. So that doesn't make a big sense out of it. The next is cells or modules of same rating but different manufacturer. Suppose in case if you try to connect two modules of different manufacturer, there may be an issue. Okay, but then it can be easily avoided by not doing so. It's not recommended always to connect modules of different manufacturers. So that is also not at all a serious problem. But coming on to the third problem is the very important problem. So different outside conditions called partial shading. As I first mentioned on the first slide, everyone will try to install a PV plant where there is no shade. Yeah, everyone will try to do that. But what will happen on the time being? There may be plants which will be coming nearby your house. There may be building coming over your house. There may be few towers which you are not aware or we cannot control. Not aware means we can't control it. In case of a large power plants, there is a possibility of movement of clouds actually. And sometimes we may not like to cut the trees which is actually there on the falling on the PV plant due to various reasons. We can't tell. So the third one is the very important one, and we actually also have learned that the characteristics of the PV module change very drastically with respect to irradiation. So that means if there was a shade, the characteristics of one module will differ from the other to a very large extent. And there is another very important thing which actually seen in countries like as India, we have seen, we may not believe it actually. You know that cleaning of PV modules, they will clean actually the PV modules for dust actually. So at that time, people may not actually clean it properly. In one module, they will clean very well. In other module, they may not clean. There may be some dust accumulating on it. And that is also affect the PV modules in a very large extent. So, yeah, it's clear. It's clear that the earlier assumption is not true always. When we connect two modules in series, it's not always their characteristics will match. So now it's us to analyze when two modules having different characteristics are tied together. So these are two modules which are tied together. Say, assume this is module 1 and this is module 2. So they have different shading patterns. So this is shaded. Assume that M2 was shaded. I'll simply say a simple analogy to that. It's like, no, there are two persons who are tied together. The two persons are tied together. One can run 1 kilometer per hour. So one can run 1 kilometer per hour. But the other can only run 2 kilometer per hour. Okay. So one can run 1 kilometer. Say the shaded cells can only run at 1 kilometer per hour, and the other model has capable of running at 2 kilometer per hour. Unfortunately, we tied them together. So both are tied. Okay, so both the persons are tied by a knot. So he is one person, he is another person. So can you imagine what will be actually the speed of both the person? This is one of the analogy which we can use it to know how does they function. So similarly, coming on to here, coming on to a PV model, assume that it's just an assumption. One person can take a current of 5 ampere. The other person can have a current of 3 ampere. And they are tied together. They are tied together. And as an electrical engineers who are actually participating, you all know that in a series connection, the current has to be same in the module 1 and module 2. The current has to be same in module 1 and module 2. But this person is able to give up to 5 ampere, and this person can give only current up to 3 ampere. So now the simple question to is, who will decide the current? Right? Who will decide the current in a series path? Right? And you can also use this analogy to explain, to understand that. To your friend and you are there, your friend is able to run at 1 kilometer per hour and you able to run at 2 kilometer per hour. You are tied together. Then what speed you may try to run is a very important question. What speed you may try to run? We may try. Who will decide? That's a very important story. Who will decide? The weaker person will decide the net speed. The weaker person will decide the net speed. So, what will be the speed? We can only run at 1 kilometer per hour. We can't move more than that. There is no doubt about it. Similarly, here, I can go up to 3 ampere. Up to 3 ampere. Yeah, fine. I can run by 3 ampere. But what's the problem? Assume that this is a very important assumption we make. There are panels which are connected. Say there are a lot of panels which will be connected like this. Say there are 10 to 18 panels are connected like this. All are capable of running at 5 ampere. Whereas only one person who is able to run at 3 ampere. Then what will happen? Everyone has to slow down. Only this person will decide the current. He is the person who will decide the current, and that is 3 ampere. Now you can tell what is actually the first problem which will actually happen. What's the first problem? You understand that the effect of partial shading. What's the problem? The problem is, as I am running at 3 ampere, I am losing all the power. I am losing all the power which it can be given by these all modules. There is a large reduction in power. The power is reduced. There is a large reduction in power. Okay, fine. Yeah, there is a large reduction in power. Do you have any other issues more? Sometimes people doesn't mind that when the power is alone reduced, but does it make any more sense out of it? Okay, I first told that there is one master for us. Hope you would have understood it, right? So hope you would have understood it. The understanding is, what you want to understand from here is, when you connected modules of different characteristics in a series, the lower current panel will decide, lower watt module will actually decide what is actually the current, and we will lose its power. Okay, so lose the power. So now the question is, I will come to an interesting point. We'll go to that later. So there are 2 modules here. And I told there was one master. Okay, there was one master to you. And this is called MPPT. Okay, right? Okay. See, now this master is telling, no, say, I will come to that point. So they are 100 watts. So they are 100 watts each. They are 100 watts each. So we will get 200 watts out of it. So when I add it, I will get 200. But assume that now it is actually a weakest panel and it has become 40 watts. Because it is shaded, it can only give me a power of 40 watts. Yeah, I'm sorry. First, let us assume that it is able to give you 80 watts. Okay, first let us assume that it is giving 80 watts. So what will be my total power? As I earlier said, the operating point will be decided by the weakest panel. The operating point will be decided by the weakest panel. And I will get what? 80 plus 80 equal to 160 watts. So 80 plus 80 is 160 watt. There is no problem. So 160 watts is what I will get it. But at the same time, if you feel that the lower panel can give only 40 watts, so the lower panel can give only 40 watts. So what is the net output? What is the net output I will get? What's the net output I will get? The lower panel will give 40 and the upper panel will give me 40. So I will get 80. So now the master has a thought. Now the master will have some thought. That thought is a very simple thought that an individual model itself can give me 100 watts. If I try to tie the other person with a 40 watts, I am getting only 80 watts. Okay, so when I am tying it, this to be 80 watts. Why can't I get it only from this panel itself? That is the thought which the MBBT will get it. Why can't I operate at 100? I can operate at this particular place and get it 100 watts. So at that time, what will happen? This MBBT will try to change its operating point from 3 ampere to 5 ampere. Okay. So we will see that what will actually will happen if an MBBT or if we try to move or if we try to operate the current which is more than that the shaded panels can give. Then we understand what actually will the problem is. Okay. So there is a possibility that the MBBT will try to increase the current. So when the MBBT try to increase the current, what will happen? So that's a very important phenomena which actually we will learn. Okay, so we understand it. There are and these are few examples of shades. So how does shades comes? People may ask. You see here, this is a very important thing for a protection. People have put like this. So that itself is a shade to itself, and a shadow of its own elements. Sometimes shades will do, though they keep but there will be shades coming on there. And a lot of trees, dust accumulation may not be uniform. So there are a lot of reasons why actually these two panels can actually differ. So there is no question on it whether they really differ or not. Okay, so they really differ. So we will actually see, in a mathematical way, how actually they will, the characteristics of the strings looks like, what will actually happen to one another. Okay, right? So now see here, there are two things I have taken. So characteristics of two panels are not same. So this is say it is a model 1. So this is model 1 and this is model 2, and this is for M1, this is for M2, and this is for M1. Okay, so you can see that their characteristics are not same. Okay, so they differ in short circuit current. So you see they differ in short circuit current. They differ too in voltages. Okay, so now how do I draw? So that's a very important thing. If I know how to draw it, then it's very simple. So we will understand that what will happen to actually the modules, right? Yeah. So we'll just understand how to draw. These are the two characteristics. So this is M1 and this is M2. So here it is M2. So M2. This is M1. Okay, right? So they are connected in series. That's a very important point which we know. So which is same? This will be same. This is a very important observation. This is I string. So I string is equal to IPV1 plus IPV, and 1 is equal to IPV2 because they are connected in series. So we can draw points. Draw point for current is equal to 0. So what will be the current is equal to 0 line? This is the current is equal to 0 line. So what will be the voltage of the string? So what will be the voltage of the string? So it is sum of the voltages VPV1 plus VPV2 when actually the current is actually 0. So this is a point. Okay, so VOC module of 1 and VOC module of 2 added together will actually give you an operating point. Okay, this is an operating point. Next, take some other arbitrary current. We take some other current, add these two voltages, and make a point over here. So similarly, if you try to draw, we will get a curve. Okay, so next point. So next point I am taking here. You see here, this is the point where I have taken here. This is the current. So when they are 5 ampere, I have taken the current. So I extrapolated like this. I find out two voltages. I find out two voltages. These are the two voltages, and I added. Right? So next, this is the operating point. Next, this is the operating point. So this is the you observe very carefully. This is another operating point, which is equivalent to the short circuit current of the shaded panels. That means it reached its maximum. The shaded panel reaches its maximum. Okay, its maximum. You see here, it is short circuited. It is almost dead. At this particular operating point, it is almost dead. Okay, shorted, dead shorted. So at that time, the voltage of the string will be equivalent to the model which is not shaded. So that's why we got this operating point. Now the question comes. What will happen if I try to increase the current further? What will happen if I try to increase the current further? That means more than the short circuit current of the shaded panels. And who will do that? You know that the person who will do it is an MPPT controller. So in case if you try to increase the current more than the short circuit current of the shaded panel, you would be able to see. You see here, this is a very important observation which you have to keep in mind to understand what is the effect of partial shading. See here, this is the current I am looking. This is the current I am looking for in this current. You see here, when I draw lines, here the module 1, which is fresh, has positive voltage, whereas the shaded module, you see, in the shaded module, the voltage was negative. The voltage was negative. The voltage was negative. This is a very important observation. The voltage was negative. So what will actually happen if the voltage was negative? What does it mean? What does it mean? The voltage was negative and the current was positive. Okay, so the power is minus V into I. So what is doing? What is actually doing? It's negative power. So if it is negative power, it means that it's acting as a load. It's acting as a load. So what do you mean that it is acting as a load? If it is acting as a load, it will start heating. Once it starts heats, if you try to continue, it will start to burn. This particular phenomena is called hotspots. Okay, so this particular phenomena is called hotspots. When you try to make the current more than that of the shaded panels, the particular panel will act as a load. As it is acting as a load, there will be heat, and this heat will try to accumulate it and try to burn itself. Very, very important one of effect of partial shading. The earlier one which we have seen is it reduces the power. That's okay, fine. But then here, the other effect of partial shading was it will kill itself. That means the particular module which is actually will be shared there. There's no way out. We have to solve it. Kill the panels by itself. Okay, so that's another effect which we have seen. So this is actually the curve which will come. You can see when you add this curve will be looks like this. Okay, so now how do you solve this problem? That's a very important thing. Yeah, I understand that when I go any current which is more than, so any current which is more than the short circuit current of this particular module, it is becoming negative. It's becoming negative. The voltage here becoming negative. VP2 become negative. So VP2 become negative. VP2 is becoming negative. How can I address this problem? How can I address this problem? I don't want my module to get killed. Right? But one thing which I understand is, I understand that the voltage across the module is going negative when it is going to die. That's another observation which I got from it. So if I doesn't allow it to go to negative, then I can save the panel. So that's very interesting stuff. That's why we do have a switch, which actually will be here. Is a diode. Is the diode. So there was a diode. We'll try to put it. At any point when the voltage become negative, right? It will try to conduct. So it will try to conduct and it will try to bypass it. Okay, so that's called that's the effect of positive shading, and that how the bypass diodes will actually try to conduct it. So whenever there is a negative voltage here and there is a positive voltage here, then the diode will try to conduct. But other times there will be positive and negative that can safeguard this particular module from the effect of positive shading. Yeah, of course, all the scientists or all the engineers will try to solve one problem, but then it leads to the other problem. Okay, we solve the problem by putting a bypass diodes, but whether it does affect the characteristics of the PV module or not, or the PV string or not, that's a question. Okay, so a little bit understanding what we got is here. Whenever the I string is greater than I shaded, module is forced to operate in a reverse bias condition, and further the power generated by the shaded module become negative and the power is dissipated, and that makes the hotspots. Right? So yeah, very simple understanding of bypass diode is used to avoid the formation of hotspot in series connected diodes. It's connected anti-parallel to the solar panel. You can see here there are anti-parallel. It is connected. Normal operation, the bypass diode operates in reverse bias condition. When a series connected module is shaded, the negative voltage appear across it, and it gets forward bias, and it will safeguard this panel from not going negative. So we'll avoid hot spots by using bypass diodes. And this is how a bypass diode can be used to mitigate hot spots. Okay, right? So now when I put a bypass diode, what will happen? That's a very interesting observation. Whether it will change the characteristics or not. Okay, so whether it will change the characteristics or not. So we will see actually. So we can see here up to the short circuit current. Up to the short circuit current, there is no change. Up to the short circuit current, there will be no change. But once it is short circuited, once the current on the string is greater than the short circuited, the circuit looks like this. The circuit will become like this. The circuit will become like this. And this is more or less equivalent to VPV1. So that's why you see here, up to short circuit, it is an additive. Up to short circuit, it is additive. After short circuit, after the more than the short circuit current of the PV model, it looks like the other model. Okay, so it has the characteristics of the other model. Okay, so that's observation, we got it. And now when you try to do this, you can see the characteristics of the PV. So far, we have seen only one peak in the characteristics. But now you'll be able to see there are two peaks. This is one peak and this is another peak. So that's the problem which actually the bypass diode has put it inside. Of course, the bypass diode has solved the problem of what? Formation of hotspot. But the bypass diode has induced another problem to the characteristics of the PV, that it looks like it has multiple peaks. Okay, so to summarize it, so you can see that this is with bypass diodes, this is without bypass diodes. This is without bypass diodes, there is only one peak, but when there is bypass diodes, it has multiple peaks. Okay, so to summarize, I think partial shading can be caused by shadows of beside buildings, trees, and poles. The output power of a PV string decreases considerably when one or more of the modules in the string are subjected to shading. Partial shading damages the PV cells module apart from reducing the PV output energy. And we have learned that how can we mitigate it by bypass diodes are connected in anti-parallel with the module to impede the hot formation. And under partial shading condition, the activation of bypass diode, multiple peak will occur at the string PV characteristics. So this all will summarize. I have something more. So Asha, can I proceed it or I can stop over here? Dr. Asha?
Hello, sir. Sir,
So can I take some more time or no, I have to stop here? I don't know.
you can take, sir. Actually,
Okay.
some questions are also there which are given by the participants. I will share. You can take, sir. You can speak, sir. Yeah.
Okay, a few more minutes.
Yes,
Okay, right. So just to explain to you, so what is actually what is some of the work which we have done on it? See here, this is an array. This is an array. Assume that all are having 100 watts at 1000 watt per meter square. So everyone is 100, so 9. So 9 into 100 will give you 900 watts, and that's a peak. So they are all connected in parallel because they are for whatever may be the performance, they can be equivalent as 300, 300, and 300. So we have 900 watts. So now what I done is I have shaded it so that it can give only 70 watts. Okay, each can give 70 watts, whereas this can give 100 watts. Okay, so the problem is, as this is the weakest person in sitting here, these three combinedly can give only 210 watts. So 210 into 3, 210 into 3. So everyone can give 210. So this is 210 and this is 210 can give only 360 watts. What is the another way out? Okay, gentlemen, we two are running good. So you don't want. I don't want this. So in that case, I can have only 600 watts. Okay, so this is so I just made a different diagram. Here also there are 3 modules are shaded. Say model 1, model 2, and model 3 are shaded. But what I made is I made each individual weak person in a single group. So this is one group. Every group has one weak person and 2 good person. So what will happen next? It is what? 200, 270. This group also work at 270. This group also 270. So there is no problem, 810 watts. So if you individually add this, that also 810 watts. So what is my understanding over here is, so in the earlier diagram also 3 modules are shaded. In the below diagram also 3 modules are shaded. But in the next diagram, I would be able to extend 810 watts. But in the above diagram, I would be able to get maximum 630 watts. So this is these two figures is the very big motivation figure for us. And what's the information which I got from these 2 figures is the very important observation. I think what may be the observation which we have got. Anyway, I have only less time. I'll move fast. See, similarly, I have done various characteristics by different, by shading different things, but I end up with in somewhere I got more thought. So the observation which I got is, this is a very important observation which we understand. The mismatch loss due to partial shading is not proportional to the shading area. That means it is not depends upon how much panels are shaded, but it depends on the shading pattern. That means how does the pattern looks. This is the important thought actually which motivated us. So that's what understanding we got from here. See, here also 3 modules are shaded. In the down panel also 3 panels are shaded, but in the third diagram there is no mismatch loss. Even the individual power, if you add, it will get 810 watts. If you combine it also, will get 810 watts. There is no loss at all. So we thought, can we able to do anything? Okay, so that's the important observation we got, but then how do you put it there in the PV array? How do you solve this problem? That's the thought which we have in our mind, and then we are actually working on. When we actually are working on it, and we got an interesting idea. Now some people, some of our students are actually solving a puzzle called Sudoku. Actually. So one time it made our mind, okay, the Sudoku is the best pattern which we can try actually. So that's how actually we thought, and we actually implemented this particular, a PV array in a Sudoku puzzle. So if you see the Sudoku puzzle, you can actually see these numbers are right, disarranged like anything. So 1, 2, 3, 4, and all the numbers are dislocated. So we've taken a 9 into 9 array. See here, this is the simple TCT array. And we actually connected like this. You can see it like this. So electrically, they are equivalent to TCT. Electrically, they are kind of equivalent to TCT, but physically, they are moved in a different place. So 2, 2. So electrically, they are correct, but physically, they are at another place. So we wired like this. So when we wired like this and try to apply shadings. So we try to apply shadings. So the different types of shading which we have done is, this is one type of shading, this is another type of shading, this is another type of shading, and anything, many, all types of shading which actually we actually tried it. And you see here, this is actually the real shading, and this is the real shading for our panel. But you see, electrically they will be distributed. As electrically they are distributed, you can see that our Sudoku puzzle, the Sudoku puzzle GP is here. We would be able to extract more power during a partial shading condition. And another best thing which it is out of it is it has only one global peak. You can see that all other TCT configuration would have only GP over here, and even it has moved from everywhere. It has multiple peaks, and GP was here. You see here, individually, even if you add, this power is 4586, but Sudoku would be able to get power of 4532, very near to what is equal to DMBPT. Whereas TCT can only take power of 3348 watts. Okay, so this is what the observation we tried for all. In all the cases, we were able to see that the Sudoku puzzle would be able to do a better, can perform better, and able to extract more. This is one of the type of reconfiguration. And I think following this, there are a lot of literatures which has been come. Many one are following many types, but the idea is to how to distribute the shade. If you try to distribute the shade, or if you make the pattern different, and then we will be able to get better power, or more power than the earlier one. And this is how we actually solve the problem, by using some rearrangement scheme. And there may be question that how to make it. This is only 9 into 9 array. But we can see here we can make 6 into 6, 3 into 3. We can make 6 into 6. We can make many things, right? So there are a few limitations to that, but we have actually solved the same by using another method. So that also available in literature. You can actually go through those literature and you can find out from that. And just to make you understand, I will say how actually power electronically we are solving this problem. This is actually a centralized inverter. And we see this is what actually normally we are doing now. To see that there is some partial shading here will affect the whole string on the whole array actually. So the voltage will get reduced to this. So there is a large problem. There is a large loss to the whole central array. So how can we mitigate it? There are 4 groups, and you are the boss. And if one group is not performing well, the better way is what? Or if you club everyone together, then everyone, the total performance will be very less. So the simple way to do it, separate them out. So separate them out. Okay, so separate it, so that the problem, the one low performer which is there in the string will not affect the other string. And this is how actually, and this I'm moving a little faster. So that's how a string inverter comes into picture. You see here, everyone will have a DC-AC inverter and a DC-AC inverter. If any problems in here, any problem which is there in this module will not affect the other module. And anything here will not affect this module. They are individually. But what's the problem? But it needs a lot of power converters, more power converters for this. But then there's another solution also given by the engineers. See here. Oh yeah, let the centralized inverter be the same. Don't worry about a centralized inverter. But then only change the DC-DC converter here. So this is called DC optimizer. So you change the DC-DC converter and put a string. So that's called a multi-string inverters. Still, we can use our centralized inverters and solve the problem of partial shading. And then this is called micro inverters. So still a micro inverter is there. So each module has one inverter. Okay, so seems to be very costly effect, but I think it's also ruling the market. But you will see here, even now, our understanding is still there. You see, even a single module is equivalent to an 3. So still, whatever we have studied is still valid. We are not in a position to keep one diode for one. We can't keep one diode for one cell because one is costly effect, another one is a technical effect, technical problem, because it cannot be used as a bypass diodes. It won't bypass. So whatever we have studied still, though we have addressed it up to the module level, still the same problem is exist, but in a very smaller way. Okay, so these are the various ways how we can address it power chronically. I think with this I will conclude, and so these are a few of the references which you have. So you can go through these references. I do have some my lectures in YouTube, so you can actually see it. So these are the two purposes so which we have published on this. The next is actually we have actually solved some of the problems which is there in the Sudoku, so that we try to mitigate it, and you can actually look into that. And now I can open for any questions. If anyone has some questions which I can answer, otherwise okay, fine. Thank you.
Sir, Ilango sir.
Yeah.
Sir, few questions, few participants asked, like I just posted in your chat box.
Okay.
Yeah, you can see, sir. Are you able to see, sir?
Okay.
Yeah.
So if power setting effect is there, then how can we connect the PV modules in solar power plants? So that's the first question. If partial setting effect is there, how we can connect the PV module in a solar power plant? I don't think what's the answer. See, we have connected it, and there are partial setting effect in the PV power plant. So due to some clouds and something, it will be there, but I don't know how to answer it. I don't understand that question. So next question I can answer: what if a nighttime partial shading condition can? I use same nighttime. There is no issue of the partial shading because nighttime PV model is not functioning, so it has no effect on that. So,
Sir, sir.
Sir,
actually, in the first question, what they mean is like when you explained about the partial shading, in between only this question is posted. Actually, the participant is asking like, how can we minimize the partial shading effect? That is what. Actually, it is again a big, maybe again it is another session. Yeah, that is a question.
How can we minimize the effect of partial shading? That's one of the thing is the interconnection scheme.
Yeah.
The other thing is how to change the inverters. No, the configuration.
Yes, sir. Yeah, actually that was the
two way. By changing the configuration, by granting the array configuration like Sudoku pattern, we can actually mitigate the problem of partial shading. Next is by changing the inverter configuration. No, may centralized inverter to string and string to what? Is inverter, we can do that. That's the answer for that.
Yeah, that is what they are asking, sir. Yeah.
So there's another question, sir. I made a project with solar panel. I made it like a sunflower. It always faces towards the sun due to use of LDR. Now I am faced a problem of output power lagging. How can I fix it? What does it mean? It is always faced towards the sun. Now I am facing a problem of output power lagging. How can I fix it? That means he's not getting the expected output power. It may be due to an MPPT problem. So what's the converter which he has connected, and it depends on the load. So I think it's a problem of BPT. I don't know how, maybe I can say that his MPPT was not okay. That's the only answer for that. Instead of connecting two modules in series, if you connect them in parallel, yeah, that's a good question. Yeah, if you connect the panels in series parallel, the effect was very minimum. Yeah, the kind of minimum, because the change which is occurring in the VMBP point, due to partial shading is very low. So, but the problem is if I need a more voltage, say if I want 200 or 400, or I want to pump more voltage into the grid, I have to necessarily go for a series connection. Okay, so for a small plants, it's fine. We actually will do that. We will actually go with parallel connection of modules, and we will solve the problem. So in parallel connection, it was very minimum. Bypass diodes is not connected to all cells of a solar modules. Then how it protects the hotspot which happens in a single cell? Yeah, if a single cell was affected, the total voltage, it will be bypassed. So I think it can solve the problem. But we feel that the partial shading will be there up to the level of 1/3 of the module. If it is very minimum, then again it's very difficult. That's only can solve by proper cleaning and avoiding shading effects. So that's also a good question. How MBPT works? It's a very big one.
This is the last question, sir.
I think you can ask him to see my YouTube. So I have made it know how an MBPT will work.
Yeah. That actually I will share. I will share that thing. Yeah. So this is a kind information for the participants. Like sir already have made a detailed presentation on how this works. So I will share that link with you people so that you can see. Okay. Yeah. And sir, anything else, sir?
No, it's fine from me. Any questions I can answer, otherwise fine.
Yeah, yes, sir. Yes, sir. Thank you, sir. Thank you, sir. Thank you for such an excellent and informative.
For the patient listening. Okay, so
yeah,
I don't know whether my audio and video are okay.
Yeah, everything was fine, sir. Like that's what, sir. Thank you, sir, for such an excellent and informative session on partial shading and interconnection schemes. Okay. Basically, it started from the basics, PV, IV curves, and in detail about the effect and everything. And every participant appreciated that. Lot of like awesome explanation, like that. Lot of comments was actually popping up in the this one YouTube channel. So I think all the participants enjoyed the very informative session. Once again, we express our gratitude for accepting our request, sir, to be an expert in this STTP in your busy schedule. So thank you so much, sir, once again.
Thank you, Dr. Asha, for inviting me. So it's always my pleasure to be. Thank you.
Thank you, sir. Thank you so much, sir. Yes, sir. Yes. See, actually, this is a small information for the participants. So in between, we are mostly seeing like everybody is asking about where is the feedback form. See, please kindly listen to this. Feedback form will be shared only at the end of the session. Only at the end of the session. Okay, like almost 10 minutes before. Then during that time, kindly try to fill the feedback form. So we are actually opening it for half an hour. Okay, so during that time, kindly fill the feedback form. Fine. Thank you. We will meet in the afternoon session, which will start at 3 p.m. Thank you so much.
you.